So, welcome back after the short break. So, we are talking about the biasing of common gate and common base circuits. Now, we are going to discuss about the small signal analysis. So, let me go to the corresponding circuit here. Yeah. So, we do have common base circuit here. So, this is the common base amplifier, and this is the corresponding small signal equivalent circuit. To save some time, what I have done is that I have drawn this circuit, but I will explain that what are the things I have done. If you see here the bias circuit, in the small signal equivalent circuit, we have dropped this DC current and we consider only the resistance here R1. So, likewise here at the emitter side, the DC current we have dropped and we have considered only this R2 here. Then this is the small signal which is getting coupled through the capacitor. So, we simply have shorted it, signal it is coming to the directly coming to the emitter, and then at the base we do have DC voltage. Even if it is having Thevenin equivalent resistance, we assume that that is getting grounded by a capacitor here. So, even if you are having source Thevenin equivalent resistance, that is ignored and the base terminal it is grounded. At the collector side, we do have GM into VBE, that voltage dependent current source flowing from collector to emitter terminal, and then of course, we do have the R naught. So, that is the small signal equivalent circuit. Input we are giving at the emitter and output we are observing at the collector. In this diagram, we are showing that output it is voltage, input is also voltage. Now, we are going to analyze this circuit step by step. So, by considering this small signal equivalent circuit, let us see what are the conditions we are getting. First of all, we do have VBE, base node it is grounded, and emitter it is having some signal, and that signal is incidentally V in. So, we can say VBE is essentially 0 minus VE. So, and VE it is same as V in. So, in fact, V in is VE. So, we can say that VBE it is minus V in. So, this is the first thing we obtain. The next one it is if you see at this node, the collector node, we do have three current elements. One current is flowing through this RO, another current is flowing through this device, and then also we do have a current flowing through this R1. So, the current flowing through this R1 it is VO divided by R1. So, VO divided by R1 it is summation of these two currents. So, if I consider this is the polarity of the positive direction of the current, then this current it is VE minus VO divided by RO, and VE it is nothing but V in. So, the current flow here it is V in minus VO divided by RO. On the other hand, GM into VBE, which is now it is GM into minus V in, and the current flow here it was from collector to emitter. So, minus sign we can remove, and then we can say that the current flow it is in this direction and it is GM into V in. So, the second term here it is representing this IC current, voltage dependent current source. So, what we have it is this current it is equal to summation of these two current. So, by applying applying KCL at the collector node rather, we obtain this equation. So, if you rearrange this equation, it is having V in and V out only. So, we can write the expression of V o in terms of V in. So, with the rearrangement, proper rearrangement, what we are getting here, it is V o equals to V in multiplied by G m into R naught plus 1 multiplied by R 1 divided by R 1 plus R o. So, this relationship, it is helping us to get the voltage gain expression. So, what we are getting is that voltage gain of this circuit, it is G m R naught plus 1 into R 1 divided by R 1 plus R o. In fact, you may approximate that this 1, it is very small. So, we can simply say that this is G m into R o in parallel with R 1. And further to that, if you recall, the common emitter amplifier voltage gain, it is similar. So, and its gain it was G m into R o in parallel with R c, and R c, it is in fact R c and R 1, it is in this circuit and common emitter amplifier, they are synonym. So, for common emitter amplifier, the voltage gain, it was G m into this one, but of course, with a minus sign. So, that is the difference. So, we can say that if we can successfully feed the signal at the emitter in the voltage form, and if you observe the corresponding output at the collector in the voltage form, then the gain of the circuit, it is same as whatever the gain we can get from common emitter, except of course, this minus sign, which means that here input and output, they are in same phase. In common emitter, the input and output, they are in out of phase. In fact, if you see here, if you closely look into this circuit, for common emitter, we feed the signal at the base, and emitter, it was grounded. So, whatever the VB it was there, it was producing this active current, it was flowing through this R c and maybe R o in parallel, and it was producing the output voltage. So, here on the other hand, for common base configuration, we are feeding the signal here and we are making it ground. So, that is the only difference, how we are feeding the signal, whether it is at the base or at the emitter. Other part of the circuit, it is identical. So, that is why it is giving us the same level of voltage gain, but of course, the polarity of the input, it was different, opposite. So, that is why here we do not have the minus sign. So, that is about the voltage gain, but we need to be careful here. Here we have assumed that there is no source resistance, and as a result, we are saying that entire V in it is coming here, and then R 2 is not having any role, and then we are really not bothered about the input resistance and so on. But practically, if you see that if you consider source resistance, signal source resistance, and if you look into the input resistance of this circuit, then we will be getting a surprise. So, to get that surprise, let us look into the expression of the input impedance of the circuit. Okay. So, to get the input impedance, what we can say, if I stimulate the circuit by say V in, and then if we observe the corresponding current here, say I in, and then if I take the ratio of V in divided by I in, that will be giving us the input resistance. So, if you see that I in for a given stimulus of V in, it is having three components. One is this current, another one is this current, and the other part it is going together, finally it is going to the ground and then it is coming back to this ground. So, the first part of this current of this I in, it is V in divided by R pi. So, voltage at the emitter node we do have V in here. So, naturally this current it is V in divided by R pi. So, likewise the second part it is V in divided by R 2, and the other part whatever the current is flowing, it is same as whatever the current is flowing through this R 1, and incidentally this current it is V o divided by R 1. So, that makes our analysis simple. So, the third part of the current it is V o divided by R 1, and we already obtained the expression of V o in terms of V in. So, this is the corresponding expression. So, we can plug in that expression here and we can say that I in it is V in, it is a function of V in multiplied by 1 by R pi, and then we do have this part, the middle part, and the third part it is we need to consider, which in my equation, previous equation I have not considered. So, we can consider this part also. So, if I take the ratio of this V in and I in to get the input impedance of the circuit, what we are getting here it is R pi coming in parallel with this impedance, namely R 1 plus R o divided by G m into R o, right. And then of course, we do have this R 2. In fact, if you look into this circuit carefully, the input impedance is having three parts. One is this conductance, and the conductance through the active device. So, this is the R pi and this is the R 2, and the middle portion if you see, if you further simplify, it is R 1 plus R o divided by G m into R o, and if you further simplify it, you may say that this part, in case if it is dominating over R 1, if I consider this is much higher than R 1, then you may approximate that this is 1 by G m. So, why I am writing like this? Because to indicate that the typical order of the magnitude of this input resistance, it is 1 by G m. So, if 1 by G m it is coming in parallel with R pi and R 2, this 1 by G m it will be dominating. Typical value we already have seen before, that this may be in the order of say 25 ohms, and on the other hand R pi may be in the kilo ohms. This resistance, depending on what kind of biasing arrangement we are considering here, this may be higher than kilo ohms. So, we may say that input impedance it is quite low, it may be in tens of ohms. Okay. So, depending, of course, it depends on the DC condition, but important note is that the resistance is very small, and whatever the if I consider the source resistance, then this input resistance and source resistance, it will be making this voltage coming to the emitter of the transistor very weak. So, we will see that what may be the consequence if I consider source resistance of this circuit. So, basically we like to say that this voltage gain, it will not remain so nice. In fact, voltage gain from emitter to output, it will be having the same expression, but from the primary input to the emitter, because of R s and input resistance here, there will be a big attenuation. So, if I call this is V in followed by say resistance of the signal source R s followed by the R in. R in is the equivalent input resistance we or just now we have derived. So, if I see the signal here, if the value of this R s it is much higher than R in, the signal here it will be very small. So, as a result we have to consider another attenuating factor. So, we will see its consequence. Before that, let me consider the common gate configuration, because whatever the analysis we have done so far for the BJT version, quite an extent it is applicable for the common gate amplifier. So, let me go into the common gate configuration. Yes. So, in our previous analysis, namely for common base, we obtain this relationship V out to V in, and here we do have the common gate configuration. So, this is the main transistor, signal we are feeding at the source through the capacitor. Gate is biased at DC voltage, and then at the drain we are observing the corresponding output. So, here we do have the small signal equivalent circuit. Again same thing, this bias circuit we have dropped in the small signal equivalent circuit. Similarly, this bias circuit, the bias current, DC bias current, it is dropped. We are just keeping only R 2 and R 1 here. The small signal equivalent circuit of the MOS transistor, it is given here by Gm into Vgs, that is the drain to source signal current, and then we also have Rds here. Of course, we do not have R pi here, and then voltage here from gate to source, it is Vgs. So, instead of Vbe in whatever we have seen for common base configuration, we do have Vgs, and instead of Ro we do have Rds. Rest of the things are similar. So, whatever the previous circuits analysis we have done, that can be utilized, namely to get the voltage gain of the common gate. So, for common gate configuration, the input to output gain, it is Gm into Rds. Instead of Ro, I have to consider Rds plus 1 into R1 divided by R1 plus Rds. Again, this can be well approximated by ignoring this one part with respect to Gm into Vgs, and it can be written as Gm into Rds coming in parallel with R1. This is again it is having the similar gain of common source amplifier, where the expression of the gain, it was Gm into Rds into Rd, but of course, with a minus sign. Here we do not have any minus sign here, rather input and output they are in same phase. Now, similar to the voltage gain, the expression of the input impedance of this circuit can be obtained from the derivation of the common base circuit. So, this is the derivation we already have out of the common base circuit. Of course, there we are having R 2 also. Now, if I consider common gate, so common gate circuit configuration, there the input resistance R in, which is defined by V in divided by I in, where V in we are applying here, and then the corresponding current here, it is, we call this is I in. So, this current this ratio can be obtained from the same analysis whatever we have done, except we have to make this is infinite, and we have to make this is RDS. So, this is RDS and this is also RDS. So, that gives us the input resistance expression. It is R1 plus RDS divided by GM into RDS plus 1 in parallel with R2. Again, here we can approximate this input resistance by 1 by Gm, and even though this 1 by Gm of MOS transistor and BJT, they are having a different order of magnitude, but still 1 by Gm it is quite low. So, since the input resistance it is low, the same problem it will arise if I consider source resistance, signal source resistance Rs, and this voltage signal it will be having difficulty to reach to the common source. So, if I consider say this Rs here, what kind of voltage gain will you get? So, let us see what will be the voltage gain if I am having this finite value of the source resistance. So, this is the corresponding circuit here. The analysis it is very similar for common base and common gate. So, let us start with the common base. So, this is the corresponding circuit. We already have discussed this circuit before. Now, if I consider along with that, if I consider it is having a source resistance of Rs, and this circuit it is having input resistance looking into the source node R in, which is we already have discussed that this is R pi coming in parallel with R2 in parallel with R1 plus RO divided by Gm into RO plus 1. So, the attenuation coming from this network, namely this V in, part of the V in it is arriving here, and the signal coming here it is, I should say, V in multiplied by this resistance R in divided by Rs plus R in. And after that, from this point to the output, whatever the gain we are having, that remains the same, and we know that the gain from source node to collector node, its gain it is given here. So, the overall gain from the primary input to the primary output, it will be this attenuation factor multiplied by this gain. So, we can say that the overall gain VO divided by V in, it is Gm R naught plus 1 into R1 divided by R1 plus RO multiplied by this part, where this is the R in, this is also R in. Now, it will be having a serious problem, and we already have discussed that this can be well approximated by 1 by Gm. So, likewise this is also 1 by Gm, and if this Rs it is significantly large, then we will be having an attenuation here, which is 1 by Gm divided by Rs plus 1 by Gm, right. So, that gives us, so this is coming 1 by Gm into Rs plus 1. So, there will be huge attenuation depending on the condition. If the Rs, if the Rs it is sufficiently large, then there will be large amount of attenuation. As a result, the voltage gain, this circuit may not be really working as a voltage amplifier. In fact, this is true for the common gate configuration as well. So, even if I consider common gate, the analysis it will be similar. Only difference is that we will not be considering this part, and then we have to consider RDS instead of RO, because for common gate this is RDS and this is I should say it is infinite. So, this is RDS and so and so, but the consequence or the overall conclusion remains the same, namely this circuit common gate also may not be a good idea to utilize as voltage amplifier. Okay. So, what may be then the other alternative? Can I use this circuit as current mode amplifier? First of all, for current mode amplifier, what we are looking for, it is idealistically the input resistance should be as small as possible, output resistance should be as high as possible, and we already have seen that this circuit is having input resistance quite low. So, we already have this property. Now, we can see that do we have this property. So, in the next slide we can see that what is the expression of the output resistance of this circuit. Okay. So, let us start with the common base configuration, and in fact, the analysis it is similar for common gate also, and let you consider finite value of this R s. So, we are keeping the source resistance R s, and this is the corresponding small signal equivalent circuit of the common base amplifier. To find the output resistance, what we are doing here, it is we are stimulating this circuit by a voltage called V y, and then we are observing the corresponding current I y. And if I know their relationship, then from that if I take the ratio of this V y by I y, that gives us the output resistance. So, the output resistance it is essentially V y divided by I y. Now, in this circuit, if you look at this circuit carefully, it can be simplified. Say this part, it is a parallel branch to ground, whereas this part it is another branch. So, whatever the resistance we can get out of this lower part, if you analyze this part, and then if you find its corresponding resistance, and then that resistance if you simply make a parallel connection of this R 1, that gives us the overall resistance. So, to simplify the analysis, probably we can presently let you drop this part and let we analyze only this lower part. Further to that, this R 2, R s and R pi all are connected to the emitter node, and the other end of those resistors are connected to ground. So, all of them we can say that they are parallelly getting connected, and equivalently you can say that from the emitter node we do have a resistance which is R s in parallel with R pi in parallel with R 2. So, in summary, if we drop this part and if we club all these three resistors into one, then the corresponding circuit it becomes very simple like this. So, let us analyze this circuit and then let we consider this is our stimulus and this is the corresponding observation, and then from that whatever the V y divided by I y will be getting, we call this is a R out maybe dashed. Then the total resistance here, of course, this will be this R out dashed in parallel with this ignored part, this one. Okay. So, let me do this analysis, and then finally, to write the expression of output impedance, we will be considering this R 1. So, in the next slide we will be analyzing this circuit. So, you do have the circuit copied here, and this is R pi in parallel with R s in parallel with R 2. Now, how do we find the relationship of this V y and I y? First of all, the voltage here it is at the emitter, it is V e, and the current here it was G m into V b e, and V b e it is essentially minus V e. So, we have dropped the minus sign here, and we have changed the polarity of the current here. So, the current flowing from emitter to collector, it is G m into V e. And so, here if you see this current I y, it is probably it is going through this part, and finally, it is coming back here. So, the current flowing through this total resistance here, it is also same as whatever the I y we do have. So, we can say that the voltage V e, it is I y multiplied by this resistance. So, the first equation we obtain here, it is V e equals to I y multiplied by the total resistance. On the other hand, if you see at this node, we do have the different. So, at this node, if I apply say KCL, what we are getting here, it is I y, it is summation of this current and this current. So, the current here flowing through R o, it is V y minus V e divided by R o. So, that is this part, and then the current here it is in this direction from emitter to collector, it is G m into V e, or you may say that collector to emitter, it is minus G m into V e. So, the I y, it is having this expression. So, what we have here, it is I y, it is written in terms of V y and V e, whereas V e it is written here in terms of I y. So, if I combine these two equations, this equation and this equation, what we get here, it is V y equals to I y into R o plus I y into the total resistance here plus I y into the total resistance multiplied by G m into R o. So, if you see that various terms here, in fact, the voltage V y, if you see here, it is having this drop and also this drop. So, this drop, it is straightforward. In fact, if you see here, this is this part, this drop, and then if I combine this part and this part, that gives us the drop across this R o, because this current is also flowing through this, and this current, it is its expression, it is G m into this resistance multiplied by this R e. So, that gives an idea that the voltage here, it is having this I y multiplied by a big resistance here. In other words, if I take the ratio of V y divided by I y, what we are getting here, it is having this resistance in series with this big resistance. In fact, compared to this part, it is very small. It is rather, I should say, this is dominating. So, we may approximate this by R pi in parallel with R s in parallel with R 2 into G m R naught. So, if you observe carefully, this R s, even if the R s it is not very big, but whatever the value it is there, that is getting multiplied by Gm into R naught. So, even if I say that Rs it is not so big, and whatever the value we do have, since it is getting multiplied by Gm into R naught, which is intrinsic gain of the amplifier, that gives the output resistance very high. At least from this part the resistance is very high. So, now to get the output resistance we need to consider the other part, namely R 1 part. So, that is what we are summarizing in the next slide. So, what we have said is that we already got the expression of Vy divided by Iy. So, it is having the impedance coming from this part. So, that is the impedance it is given here, and then we do have R 1. So, the output impedance of the circuit, it is whole thing in parallel with R 1. So, I should say that this common base configuration, this portion it is having very high resistance. Now, if this bias circuit it is also having high resistance by implementing say by active device, then you can say that its output resistance is very high. Now, whatever the analysis we have done, that can be utilized to get the output resistance or output impedance of the common gate configuration also, namely the MOS counterpart, and its output resistance it will be obtained from this expression only by dropping these parts and replacing this R O by R d s. So, I am just writing that R 1. So, this is the output resistance of the common gate configuration, R 1 in parallel with R d s plus R s in parallel with R 2 plus R s in parallel with R 2 into G m into R O, right. So, again the output resistance here it is high. So, we are convinced that for common base or common gate the output resistance is very high. So, let us see this circuit either common base or common gate as current amplifier. So, we do have the corresponding analysis to find the expression of the current gain. So, here we do have the common base configuration, we do have the corresponding circuit here, and to get the current gain what we have to do at the output node, we have to make the corresponding terminal unloaded. What do we mean by unloaded? We have to basically short this node to AC ground, and then we have to find how much the current it is coming from the circuit, signal current. We are putting this capacitor so that the operating point of the transistor it is not getting affected, and at the same time signal wise we are observing the short circuit output current. And we know that if the signal it is in current form, unloaded condition should be the corresponding impedance or the terminating impedance should be 0. So, small signal model if you see the corresponding situation here, it is this node, the corresponding collector node it is ground, and we are observing the corresponding signal current I naught. For the input signal it is I in. In fact, in this case we are stimulating the circuit by signal current. Now, if you see this circuit, again the base node it is grounded, voltage at the emitter we do have V e. So, the V b e it is V b e it is minus V e, right, and part of the current is also flowing here. So, we can say that I in it is having different component. One is this part, another is this part, right. And then we also have this current and this current. So, the if you see one by one, this current, it is Gm into VE. So, that is why Gm into VE is the first part, and then the second part here flowing through R pi, it is voltage here VE divided by R pi. So, that is the second part, and then we do have this part, third part, which is VE divided by RO, and then through this bias circuit, which is VE divided by R2. So, in summary, we can say that I in, it is it can be directly written in terms of VE. On the other hand, if you see the current at the output terminal here, so if this is the current, in fact this current, of course, this node it is grounded. So, the current here it is actually 0, because this is also ground, this is also ground. So, the current here it is 0. So, the I naught on the other hand, it is summation of only these two currents. We do have this current and we do have this current. So, I naught it is V into Gm, and then we do have V divided by R naught. So, if I take ratio of these two, what we are getting here, it is the V this is getting cancelled. So, the current gain I O divided by I in equals to Gm plus 1 by R O divided by Gm plus 1 by R O plus 1 by R pi, and then plus 1 by R 2. In fact, if you see, because this Gm it is dominating, we may consider rest of the things it is very small. In fact, you may call this is practically it is Gm by Gm. If you want, you can probably keep this part, or to be more precise, it is we may drop this part. So, we can retain this part and we can retain this part. So, it will be Gm divided by Gm plus 1 by R pi. Of course, this R 2 can be ignored. Definitely, it can be ignored with respect to Gm, but whether this is ignorable with respect to R pi or not, that depends on what kind of biasing arrangement we do have for the emitter terminal. But whatever it is, we can write in this form, and you can further simplify this as Gm into R pi divided by Gm into R pi plus 1. In fact, you may recall that Gm into R pi is nothing but the beta of the transistor. So, this is beta divided by beta plus 1. In fact, you may recall this is nothing but alpha of the transistor. That is very obvious. If I ignore this resistance, if I feed a signal current here at the emitter, whatever the current we will be getting at the collector side, it depends on how much the current gain we do have from for this transistor from emitter to collector, and that is nothing but the alpha of the transistor. So, we know that this alpha it is very close to 1. So, we can say that this current gain it is less than 1, but it is very close to 1. So, that gives us a good conclusion that this circuit, namely the common base, since its input resistance is low, output resistance is high, and the current gain it is close to 1. So, it is a good circuit for current mode buffer. The similar kind of analysis it can be done for common gate also. I think you can do yourself just by dropping this part. For that, for common gate we simply remove this part and that gives us the corresponding current gain I out divided by I in equals to G m plus 1 by R naught divided by G m plus 1 by R naught plus 1 by R 2. In fact, for this case it is if I ignore this R 2, then it is exactly equal to 1. That is very obvious. For BJT we do have this path which is taking some part of the current, but for MOS we do not have the gate to source resistance. So, as a result, at the source whatever the current we give, the entire current it is arriving to the drain terminal. I think most of the things we have covered. So, what are the things we have covered today? It is we have discussed about the common base and common gate amplifiers or configurations. It works as a buffer, particularly for current mode amplification. What we have covered today, it is the basic operation of these two configurations, and we also have discussed a little bit about the different biasing schemes. Numerical discussion it will be done later, and then we have done full set of analysis of the small signal analysis of common base and common gate configurations to find the gain, particularly voltage gain, input impedance and output impedance, and also current gain. So, both voltage as well as the current gain we have discussed. Numerical examples on these two configurations we will be covering later. I think that all we need to cover. Thank you.